and it will be moderated by Dr. Naveen Krishnan, Associate Professor, Division of Work Environment, Department of Community Health, St. John's Medical Hospital. Dr. Naveen has significantly contributed in the field of occupational health for best research work, and he's won the award for the best research work in the field of industrial health in the year 2009. And in 2017, he has won the Best Resource Person Award by the Indian Association of Occupational Health for his contribution in the field of occupational health. We hand the session over to Dr. Naveen Ramesh.
We'll start off today's proceedings. The first speaker is Dr. Timothy. He's a lecturer in radiation physics from the Department of Radiation Oncology, CMC VELLORE. He's a member in the Association of Medical Physicists of India, and also he owns a membership in the Association of Radiation Oncologists of India. We request Dr. Timothy, please.
So the title of my talk is Radiation Monitoring. I'd like to focus on risk reduction at the workplace. I think many of you may not be radiation professionals. So having that in mind, I would like to give a few introductory slides to radiation protection, then focus a bit on radiation hazards in the workplace. Then we'll see about the rationale for radiation monitoring, the different radiation monitors that can be used. And also, in addition to just monitoring, what else can we do using radiation monitoring in the workplace is to reduce the amount of risk to the occupational workers in that area. We also would like to have a look at the new tools that are used for radiation monitoring and see what we have to do in case there is an overexposure. So a few slides on the physics part of it and the biological effects. We know that radiation can be broadly classified as the ionizing and non-ionizing type. And we'll be focusing on the ionizing type of radiation, that is alpha, beta, gamma, and X-rays. In a hospital like ours, we use mostly gamma and X-rays, and of course, beta in nuclear medicine. The low-energy X-rays are used in radiodiagnosis, and high-energy X-rays are used in the linear accelerators in radiotherapy. Gamma rays are also used. The low-energy gamma rays like technetium-99m are used in nuclear medicine scans, and we use the high energy for cancer treatment. This is how the chain of events will pan out when a person is exposed to radiation. So you have the physical stage, which is all within the milliseconds, that is 10 to the power minus 16 seconds. So there the ionization happens and the dose is deposited or absorbed in the body. Then you have the physicochemical stage where there is an interaction between the molecules and the formation of free radicals. So these free radicals will interact with the cells and the DNA, causing a damage and leading to a biological stage where there can be cell death, mutations, change in genetic data, and this can happen from anywhere between a few minutes to many years. So what does ionizing radiation exactly do? It deposits energy that can injure or destroy cells by damaging their genetic material or DNA. You can see here that there can be single-strand break or a double-strand break, and this can happen because of the formation of the free radicals, which I mentioned in the previous slide. And you can see that this will depend upon the energy of the radiation, type of radiation, and the intensity of radiation. And biological effects can be classified as non-stochastic or stochastic effects. The non-stochastic effects are something which can be determined. So if you say that a person receives a certain quantity of dose, then that can lead to a particular biological effect. So this has a threshold. You can see here that in this graph that only after a particular amount of radiation received by a person, then there can be a biological effect. And this, of course, increases, the severity increases with the increase in dose. So examples are cataract, sterility, epilation. And the non-stochastic effect, this is more of a probabilistic or a random process where even very low amounts of radiation can lead to a biological effect. And So these are more of late effects as compared to the early effects in the deterministic process. And the examples for this are cancers and, for example, leukemia. These were all first studied when there were the atom bomb survivors in Hiroshima and Nagasaki. The aim of radiation protection is to prevent the deterministic effect and to limit the total probability of stochastic effects to acceptable levels, and to ensure that the practices involving exposure to radiation are justified. So the system of radiation protection has three principles. One is justification. So as a clinician, we have to be justified in recommending a scan or any process which involves radiation, that is ionizing radiation, I mean by that. So there has to be a clear benefit over the risk due to radiation to that person. Then we also have to optimize. So ALARA stands for as low as reasonably achievable. So we always aim to ensure that the person who is receiving the radiation receives as low as possible. So we can always take a scan with high levels of radiation as well as low. So we have to optimize and ensure that we give the lowest possible amount of radiation and still get a good image. And we'll be seeing this. I have focused on only certain areas of radiation use, and I know that you can extrapolate it to different areas. And there are many times that a person can always say that this is the maximum limit I can, this is the maximum reduction in dose that I can achieve. So this can be very, this can be very subjective. And so a certain group can say that this is the maximum amount of shielding that I can give to these occupational workers that are working here. So we have examples in different hospitals where people were not given proper lead barriers to work in a safe environment because the management just said this is what we can do. So in order to account for these things, the numerical dose limits have been prescribed. So these are in the form of annual dose limits. So for a radiation worker, you can see that the whole body dose per year, the maximum can be 30 millisievert in 1 year, and over a period of 5 years, the average value is 20 millisievert per year. And these are supposed to the member of the public who can receive only 1 millisievert per year. So if you're thinking that radiation personnel are superhumans, we are not, because the members of public are not being monitored. So that's why we have to be extra vigilant to make sure that the radiation dose levels to public areas, even in a hospital, will be 1/20th of that dose. So we can see for lens of eye, it's 150 millisievert. This has recently been further reduced to 50. And for extremities, skin, it's 500 millisievert per year. So you can just remember one or two of the values. We'll come back to this later. And pregnancy, once declared for a radiation professional, they're not allowed to get more than 2 millisievert to the lower trunk because the fetus who will be considered as a member of public can't receive more than 1 millisievert, which is this value. Some of the radiation hazards in a workplace. So we have seen that there has been a study here which was done from 1976 to 2000 where they analyzed the incidence of cancer to personnel who are working in an operation theater. Here it was orthopedic surgeons. And they found that they were not using any proper radiation safety accessories. And you could see here that the average dose was 35.4 millisievert. But the intriguing thing was that 9 out of 31 personnel had cancer, instance of cancer in their lifetime. And if you compare it with the unexposed radiation workers, and it was around 4%, so at least 25%, so which is quite high. I know that many times we say it's just a C-arm and we use very low levels of radiation, low energy, but you can see that the risk can be quite high. And that, of course, that reduces for people who are standing away from the primary radiation. And there's one more study which found out, this was actually done using dummies of phantoms. They found that when there was no protection used, when a person was in direct contact with the radiation beam, they could receive doses up to as high as 40 millisievert per minute. So you know that for the extremities, the maximum dose was 500 millisievert per year. And you can see that will be achieved within a few minutes. So for the surgeon who will be standing, it will be 0.2. So even this, we are allowed only 20 millisievert for the whole body. So all these values can be reached pretty quickly. So that's why it's important to use proper safety accessories like lead aprons, lead flaps, and the such. Since we are also talking about the lessons learned from other industries, I just thought one of the instances that happened in France. So there was a radiation worker who walked into the radiation facility. It was a nuclear reactor facility, and they found that he had high exposure levels. So the interesting thing is you are expected to have a contamination only when you're coming out of a radiation facility, because there could have been some spillage or some kind of incident. But here, when they probed further, they found that it was not actually a contamination or spillage due to some unsealed source from the radiation facility, but it was actually emanating from his watch. So the watch had some steel metallic parts, and those parts had, the watch was made in Hong Kong, and they found that these steel parts were actually got from China. So what had happened was, there was a cobalt-60 source used in radiotherapy, high energy, high activity source, which had been improperly decommissioned, which had not been decommissioned and just sent to scrap. Just terrible. So we know that the cobalt-60 source is encapsulated using steel. And this steel, along with the cobalt source, had been melted for scrap and recycled. We say recycling is good, but it has to be done in the right way. And this ended up in watches. It's actually a watch called Trophy. So this many years back, so you don't have to worry. So it came as a news article in 2000. And even places like Ireland found that these watches were there, and many people received additional extra dose because of this. And this is one thing, no? If it was not for radiation monitoring, they couldn't have found it out. Of course, you'll ask why everybody is not going to walk into a nuclear facility, but then I'll have some answers maybe at the end of this talk. Another incident where there was a disregard for radiation monitoring. This was a HDR brachytherapy source, and this is from an example from another country. The equipment had malfunctioned, so the radiation source has to be here, and the patient will be here, and the source will go inside the patient, give the therapy dose, and come out. But what had happened was, the source wire had broken, and the source remained stuck inside the patient. And there was an alarm. So we have a gamma zone monitor, which will show the radiation levels and give an audio alarm. But that was ignored, because the unit console said the source is in safe position. So always it's good to have an independent device to verify this. But they didn't listen to us, and the patient received 16,000 gray, which is a unit of radiation, as against the prescription, which was supposed to be only 18 gray, so almost 1,000 times. So unfortunately, the patient died. And not only that, because of the source going along with the patient to the nursing home for 4 days, the source was around till they found out, and they realized that almost 94 personnel were overexposed. So what is radiation monitoring? It is to assess the workplace conditions and also individual radiation exposures to ensure acceptably safe and satisfactory radiological conditions in the workplace, which include radiation generating equipment like X-ray machines, Linacs, as well as those which use radioactive sources. So we, part of an ARB project, we had the opportunity to inspect many hospitals some years ago. And we found that when we did the measurements with the gun monitor, we found very high doses. When we investigated, we found that the plain glass, instead of using lead equivalent glass, they were using plain glass. So almost the radiation doses were 100 times more. And in certain times, almost 1,000 times. And many places use wooden X-ray barriers without the lead sheet. So these are all additional advantages. But how do we monitor radiation? Because we can't see radiation, we can't feel, or any of the 5 senses can't detect radiation. So without radiation detectors, measuring radiation is like 3 blind men searching for a black cat in a dark room. So we get nothing. So moving on to the types of radiation monitors. There are many types of radiation monitors, like ionization chambers, GM counters, Geiger-Müller counters, scintillation detectors, solid-state detectors, TLDs. These are all examples. But they can be classified as area monitors. I mentioned the gamma zone monitor, but we also have the survey meter, which is held in the hand, and you go about finding out whether the radiation levels are safe in and around a radiation facility. Then we have personal monitors. I think many of you will be aware, or you may be using one, which is used by the individual worn in person, so that we can find out what is the equivalent dose that they are receiving. And this will be compared with the annual dose limits, and every quarter they have to change the TLD badges, and we can ensure that they are kept within dose limits. And it's also important to have these calibrated. AERB is very stringent that all these monitors have to be calibrated in an AERB approved calibration facility. The other types of monitors, mainly this can be used in nuclear medicine facilities, and these are mainly used in nuclear reactor facilities, but also can be used in nuclear medicine facilities. So you have the laundry monitor, where you have personnel who can, when they change the clothes at the end of the day, if they are wearing some overalls or something, and this can be monitored. Then you have the hand and foot monitor, so you can check whether there's any contamination to the extremities, and a flow monitor in case of spillage in nuclear medicine. We also have whole body counters, where this can be useful in finding out internal contamination, internal exposure. So in case there's been ingestion or inhalation. So moving on to the impact of radiation monitoring, this helps us to audit and also optimize the dose. So we go one step further, not just keep it within limits, but also to further reduce the doses. So this can be done in all interventional places by using appropriate filters, correct exposure parameters, and also to use pediatric protocols for children. Many of the places in the country we see CT scans, adult protocols are only used. So we can also take advantage of the digital detectors, which are more sensitive. So you can give less dose and get good quality images. So we did some studies. We were able to reduce the dose in cath lab by 27 to 47%. And also this balloon mitral valvoplasty procedure, where we were able to reduce the dose levels to half with good cooperation from our cardiologists. Moving on to some new tools. What's exciting in this field is that we have systems like the teledose system, where the supervisor can monitor the levels of radiation received by different people. So this will be like a remote monitoring system. And these were used in Chernobyl reactor area, where the restoration work was going on. You know that there's a reactor in Ukraine which exploded, and still it has very high levels of radiation. So when people go into work, they will be wearing these kind of monitors, and for these kind of work, the radiation levels are so high that they will reach the annual dose limits within an hour or even less. So there will be a beep, and they have to stop working. So many people have to spend less time and get the work done. And this is something new by RaySafe, is a real-time personal dosimetry. So even when working in a cath lab, for example, you can see the online doses. And it can also tell you what is the percentage of the annual limit that you have reached. This is actually to investigate the source position monitoring. So we developed some system in CMC. So you can see here that radiation dose, though we say invisible, by using phosphors that is used as intensifying screens, we can actually see the position of radiation and verify whether the source is in the correct position for brachytherapy. One interesting thing is we always see these drones. So in weddings and everywhere, the pesky things which come and take photographs close to us. Taking the advantage of this, we can use this for radiation surveys. Because traditional detectors, we have limitations. So for example, this is a wall of a radiation facility. A radiation personnel can only find the radiation level dose at his level or below. But this can help us in finding the 3D dose maps in levels which we can't reach. And this can be very useful because not only they can go in the sky and find out areas which have been affected by radiation disaster, but also they can work over a high range of temperatures, and also they have very high sensitivity, and they will be able to relay this information through wireless transmission. So here you can see a GM counter, which I mentioned before, which is being connected to a drone. And this is something which the healthcare can also adapt in future. One more thing which was developed in CMC by one of our students, engineer, under the guidance of Dr. Abhiraj Singh, was the smartphone detector. You can see a normal cell phone, and we can use the camera, which can detect usually visible light. It's also found to detect gamma and X-ray radiation. So that is covered with a black piece of tape so that the visible light is cut off, and then you can detect the specks. So I hope you can see this. You can see here some small specks, and this is calibrated to the dose values. So we can calibrate this. An app has also been developed called Spreadet, and it's still a work in progress. So once complete, this will be able to be used by one and all, anybody who owns an Android phone, which is like millions of people. So this is one way where the common person can use a small phone which they have instead of using high equipment, costly equipment to detect radiation. And we are also developing a personal monitoring service software, which is to help us keep inventory. And one exciting thing that we have is biodosimetry. Because physical dosimeters have a limitation. They can just measure the amount of dose, but they cannot be, sorry, I'll just finish in 1 minute. And they cannot be actually related to the direct health risk. So the true dosimeter will be to use, will be a biodosimeter. In example, in this case is a comet assay, where you can see that the resulting image that is as a result of this single cell gel electrophoresis will give an image which is like a comet. So this part will be the intact DNA, and this will be the DNA fragments because of the single strand and double strand breaks. And as we can calibrate it, you can see here we can calibrate it by the length of the tail. So higher dose, longer tail. So this can be used, and we are going to start this for our radiation personnel. We are going to do some random tests and see whether it's matching with the dose received by their personal monitors. So quickly about overexposure. So if there is an overexposure and it's found to be genuine, the AERB takes immediate action. So many times we say that we get the doses very late, but actually they will take immediate action, and they will ensure that a proper inquiry is conducted to find out the reason for this high dose. And if there is a dose more than 10 millisievert, that is the limit is 20, but even more than 10, the person will have to be laid off the radiation area till they are heard. And if it's more than 100, they have to undergo chromosomal aberration test to verify the amount of dose. The RSO, the Radiation Safety Officer of the institution, also will conduct an inquiry, and this will have to be presented in the standing committee. To summarize, it's important to have a systematic radiation monitoring program, and to also audit and optimize the dose for different procedures. And calibration is very important, and it's also important to incorporate newer tech tools for effective monitoring of radiation levels. Finally, investigation, follow-up, and reporting of overexposure can play an important role. The role in the effective control of doses. It will also help create an awareness and avoid recurrence. The review of cases exceeding annual dose limits will not just be useful for the hospital, but also once reported can be useful for the whole country as well. So I'd like to acknowledge different personnel who are involved in these projects for their contributions to this talk. Thank you.